This paper was given to the American Physical Society March meeting in Denver in 2014. It describes a fundamental enhancement of quantum mechanics. Dirac wrote that the wave packet is unstable, but the next slide will show that he was mistaken. Phi represents a wave packet. In the direction of propagation, x is imaginary. As such, it forces phi to oscillate. So that if the real part represents the electric vector in an electromagnetic wave, then the imaginary part represents the magnetic force field. Let's look next at the envelope part of the wave function. It's dominated by sigma. Sigma is an experimental value determined by initial conditions and is stable during propagation in free space. And this is a consequence of Newton's first law. Likewise, the normalizing factor A is dependent on sigma and is equally stable. We're left with the exponent of x squared over 2 sigma squared. X contains 4 variables. 2 of these, omega and k, are mean values of a symmetric wave function. As such, they're stable. But the stability is guaranteed by the conservation of energy, by the conservation of momentum, and by the symmetry of space-time. We're left only then with x and t, which describe the profile of the wave group. Because all the other values are stable, the profile is itself stable. And with a stable wave packet, you can derive some physics. You can Fourier transform it and find the Heisenberg uncertainty principle. You can operate on it and find Planck's law and the de Broglie hypothesis and various conservation laws. What we did was to use the travelling wave group as a solution for the Klein-Gordon equation, the relativistic version of it. And the output is a second-order algebraic equation. Notice we've used the simplified constant c equals 1, reduced h equals 1, and in the next graph we're going to choose a value m equals 1. This equation is the same as you get if you take Einstein's equation, E squared equals P squared C squared plus M squared C to the fourth, and substitute H omega for E and HK for P. What we did next was to differentiate. And when you do that, you find a new result in relativity, that the product of the group velocity and the phase velocity is equal to c squared. Let's see how that plots out. Here's the group velocity, and it's very well behaved. It tends to 0 at low k. It tends to c at high k. It contrasts with Dirac's calculation for the speed of the electron. He calculated the speed of the electron is equal to c, and he knew this was unphysical, but he waved his hands and zitterbewegung, and you don't have to do that because you've got Vp. Well, what is Vp? It breaks the light barrier. Can you measure it? Yes, it's the inverse of the group velocity. It's also the ratio of energy over momentum. And is it real? No, the carrier wave does not carry energy, but it carries phase. It's complex. What you have to understand in the wave group is how the carrier wave crests appear, grow, pass through the wave group and disappear like will-o'-the-wisp, swapping energy but not carrying it. In the lower graph, plotting omega against k, you can compare the particle with the photon dynamics. From a stable wave function, you can make some deductions so basic they are surprising. Let's return to the algebraic equation second order, because it's second order, it has more than one solution. Dirac gave the negative eigenvalue to the positron, but he insisted it has positive mass and positive kinetic energy, and let's see what the consequences are. Here's negative energy. And at some point where k, the modulus of k equals the modulus of m, there's a singularity. And it causes the group velocity to cross the light barrier and go to infinity, and the phase velocity to go to zero. There's no experimental evidence for this. It's unphysical, and the suppositions are false, and they have to be examined. Well, what do we find? E equals mc squared. If E is negative, m is negative. E equals h omega. If E is negative, omega is negative. And if omega is negative, k is negative. Otherwise, the wave group will decay and break several conservation rules. So let's plot the result of these basic assumptions. The electron is shown in the positive quadrant and its antiparticle in the third quadrant. With a representation like this, you can again do some new physics, especially in annihilation and creation. Notice that the group velocity and the phase velocity are positive for both the electron and the positron. So now we're able to compare some properties. We have three candidates: the electron, the positron, and the negatron. The electron has negative charge, positive mass, negative E over m, and regular dynamics. This ratio E over m is very important because it determines quantum electrodynamics. We don't need to lock horns with it. We're going to take it all over by keeping this constant consistent with theory and experiment. And that's done so with the positron, and is done so with the antiparticle to the electron, which has, as we saw, negative mass and therefore negative charge. Its kinetics, as we saw, are also well behaved. Meanwhile, the positron is unphysical, and what the travelling wave group and relativity have taught you to do is to annihilate it. There are many consequences, and this is not the place to examine them in detail, but only to mention that quantum mechanics is more than a series of microbands. It is also a continuous transformation of wave functions.